I'll be telling about practical harmonic analysis. Practical harmonic analysis is a branch of mathematics that deals with the study of periodic functions and their components. It is widely used in various fields such as signal processing, physics, engineering, and music. The goal of practical harmonic analysis is to decompose a complex function into a simpler sinusoidal component. Harmonic analysis is a branch of mathematics concerned with investigating the connections between functions and its representation in frequency. The frequency representation is found by using Fourier transform for functions on the real line or by Fourier series of periodic functions. Generalizing these transforms to other domain is generally called as Fourier analysis, although the term is sometimes used in interchangeable with harmonic analysis. Harmonic analysis has become a vast subject with application in areas as diverse as number theory, representation theory, signal processing, quantum mechanics, tidal analysis, and neuroscience. The classical Fourier transformation on R power n is still an area of ongoing research, particularly concerning Fourier transformation on more general objects such as tempered distribution. For instance, if we impose some requirements on distribution F, we can attempt to translate these requirements into the Fourier transformation of F. This is an elementary form of uncertainty principle in an harmonic analysis setting. Many physical phenomena such as sound waves, alternating electric currents, tides, and machine motion and vibrations may be periodic in character. Such motions can be measured at a number of successive values of an independent variable. Usually the time and this data or a curve plotted from them will be representing a function of that independent variable. Generally, the mathematical expression for the function will be unknown. However, with a periodic function found in nature, the functions can be expressed as a sum of number of sine and cosine terms. Such sum is called as Fourier series. After the French mathematician Joseph Fourier and determination of these coefficients of these terms is called as harmonic analysis. One of these terms of Fourier series has a period equal to that of the function f of x and is also called as fundamental. Other terms has shortened period that are integral submultiples of fundamentals. These are called as harmonics. The terminology derives from one of the earliest applications, the study of sound waves created by violin. Fourier series. Fourier series is a fundamental tool in practical harmonic analysis. It allows us to represent a periodic function such as sum of sine and cosine functions of different frequencies. It is named after the French mathematician who introduced the concept in early 19th century. The Fourier series is particularly used in signal processing, engineering, and various branches of mathematics. Fourier series provides a way to analyze the frequency content of signal and extract useful information. Mathematical formulation. For a periodic function f of x with a period t, the Fourier series represented is given by this. Here the coefficient of a of 0, a of n and bn are determined through the integral involving the function f of x. The formula of these coefficients are as follows. Coefficient interpretation. A of 0 represents the average value of a function over one period. A of n represents the amplitude of the cosine component with frequency n by t. B of n represents the amplitude of sine component with frequency n by t. Applications are signal processing used for analyzing and manipulating signals in communication system, heat transfer applied in solving heat conduction problems, vibration analysis used to study vibrations in mechanical system, audio and music representing and synthesizing sound waves. The Fourier series is a powerful tool for understanding the frequency content of periodic functions, providing a way to analyze and manipulate signals in various applications. Fourier transform. Fourier transform is an extension of Fourier series for non-periodic function. It transforms a function from a time domain to the frequency domain. Fourier transformation allows us to analyze the frequency content of non-periodic signals and can be applied to the various problems such as image processing and data analysis. The Fourier transform is mathematical technique that extends the ideal of Fourier series to represent functions in the term of frequency component, even when the functions are not necessarily periodic. The Fourier transform is a powerful tool used in various fields, including signal processing, communication, physics, and engineering. Mathematical formulation. For a function f of t, the continuous Fourier transform of a for w is defined as follows. Here w is an angular frequency and it is also known as omega, and e power I minus I wt represents a complex exponential function. The inverse Fourier transform, which reconstructs the original function from its frequency component, is given by this. Interpretation. W of omega represents the amplitude and the phase information of the frequency component omega in the original function f of t. Applications. Signal processing used for analyzing and filtering signals. Communication system essential for modulation and demodulation. Image processing used in image analysis and compression. Quantum mechanics fundamentals in quantum mechanics for wave function analysis. Properties. Linearity. The Fourier transform is a linear operation. Shift theorem. Shifting a function in time domain corresponding to the phase shift in the frequency domain. Scaling theorem. Scaling a function in a time domain correspond to compression or expansion in the frequency domain. Convolution theorem. The Fourier transform of an convolution of two functions is a product of their individual Fourier transform. Applications in signal processing. Practical harmonic analysis is extensively used in signal processing. It helps in filtering, compression, and noise reduction of signals. Fourier analysis provides foundation for digital signals processing algorithms. Applications in physics. In physics, practical harmonic analysis is applied to study wave phenomena, vibration, and oscillations. It is used in analysis of sound waves, electromagnetic waves, and quantum mechanics. Harmonic analysis plays a crucial role in understanding the behavior of physical systems. Applications in engineering. Engineers use practical harmonic analysis to analyze and design systems with periodic component. It is employed in the analysis of electrical circuits, control system, and applications in music. Practical harmonic analysis is essential in music theory and composition. It helps in analyzing and understanding the harmonic structure of musical pieces. Musicians can use harmonic analysis to create complex harmonics and chord progressions. Discrete Fourier transform. The DFT is a numerical algorithm used to compute the Fourier transform of the discrete signals. DFT is a mathematical operation that transforms a sequence of complex numbers representing discrete samples of a signal into another sequence of a complex number that represents the signal in frequency domain. It is widely used in digital signals processing and data analysis. DFT allows us to analyze the frequency content of sampled signals and perform efficiently computations. Fast Fourier transform. FFT is an efficient algorithm to compute discrete Fourier transform. The FFT was developed to overcome computational inefficiency of straightforward DFT calculation, especially for large data set and enables real-time signal processing. The FFT algorithm takes advantages of symmetry and periodicity in computation of DFT, significantly reducing the number of algorithm operations needs. It follows divide and conquer approach, breaking down DFT computation into similar subprograms. Conclusion. Practical harmonic analysis is a powerful tool for analyzing periodic and non-periodic function. It has derived applications in signal processing, physics, engineering, and music. The Fourier series Fourier transform and DFT and FFT are fundamental concepts in practical harmonic analysis, enabling efficient analysis and manipulation of signals and data.